A case for kernel-level implementation of inter-process communication mechanisms. Abstract. Distributed systems must provide some kind of inter-process communication, IPC, mechanisms to enable communication between local and especially geographically dispersed and physically distributed processes. These mechanisms may be implemented at different levels of distributed systems, namely at application level, library level, operating system, interface level, or kernel level. Introduction. A distributed system is a type of parallel or distributed processing system, which consists of a collection of interconnected, standalone or complete computers, cooperatively working together as a single, integrated computing resource. The general focus nowadays is mostly on MIME model, using general-purpose processors or multi-computers. We only focus on multi-computers in this paper. In contrast to multiprocessors, multi-computers lack physical shared memory. They rather rely either on message passing or on distributed shared memory, irrespective of which one of these interfaces they provide to the programmers. They have to implement some sort of inter-process communication mechanism. The crucial challenge is how efficient these mechanisms are implemented by distributed systems, ignoring special cases where efficiency is not an issue, like in educational or research systems. Efficiency of IPC is critical to real distributed systems that are intended for high performance computing, like in scientific cluster computations dealing with compute-intensive computations. Given the importance of IPC mechanism implementation efficiency, the next challenge is how best one can attain the best degree of implementation efficiency. Backgrounds on MPI and DIPC. Message Passing Interface, MPI. The MPI standard defines a software library used to turn serial applications into parallel ones that can run on distributed memory systems. MPI has sought to make use of the most attractive features of a number of existing message passing systems, rather than selecting one of them and adopting it as the standard. MPI has been strongly influenced by works at the IBM T.J. Watson Research Center, Intel's NX/2, Express Cube's Vertex, P4, and Permex. Other important contributions have come from Zipcode, Chimp, PVM, Chameleon, and Pickle. 5. Several advantages are attributable to MPI. 1. 10. Universality, expressivity, well suited to formulating parallel algorithms. Acceptable performance, explicit association of data with process allows good use of cache. Any parallel algorithm can be expressed in terms of the MPI paradigm. Runs on both distributed and shared memory systems. Performance is generally good in either environment, allows explicit control over communication leading to high efficiency due to overlapping communication and computation, allows for static task handling, data placement. Problems are rarely observed. For suitable problems it scales well to very large numbers of processors. It is portable, and its current implementations are efficient and optimized. Distributed inter-process communication, DIPC. DIPC 2, 3, 4, was founded by Dr. Mohsen Sharafi in 1993. DIPC provides the programmers of the Linux operating system with distributed programming facilities, including distributed ship DSM. It works by making Unix system VIPC mechanisms, shared memory, message queues and semaphores, network transparent, thus integrating neatly with the rest of the system. The underlying network protocol used is TCP/IP, and it is targeted to work on WANs, wide area networks, and in heterogeneous environments. Unix is among the platforms of choice for writing parallel and distributed programs. The AT&T Unix provides what is known as system VIPC mechanisms, consisting of shared memories, message queues and semaphore sets, to enable programmers to exchange data and synchronize between processes running on the same computer. It should be noted that DIP provides a set of mechanisms, and is not concerned with policies. The software designer determines how these mechanisms are used. DIP and MPI implementation levels compared. Let us reiterate that the overall performance of applications running on distributed systems depend on the efficiency of IPC mechanisms that are implemented by the distributed systems. This is particularly true in applications or systems that need or provide high-performance computing. The reason is that computations are ideally broken down to many parallel processes by programmers to be run efficiently in a distributed fashion by the distributed systems. These processes often need to communicate to perform and complete their computations, and thus their efficiency depends very much on the degree of efficiency of the provided IPC mechanisms. The implementation of every IPC mechanism, regardless of the level of its implementation, entails one or more system calls to the operating system. Each system call traps the kernel and yields a process context switch between user mode and kernel mode. The switch is costly and has lots of overhead, so it has to be avoided as far as possible if one is interested in better system conclusion. This paper put forward the consensus that kernel-level implementations of inter-process communication mechanisms are favorable to those that implement such mechanisms at other non-kernel levels. It showed that a given bench program run in parallel in a distributed cluster in WAN is more efficient when programmed and ran under a kernel-level implementation of IPC, namely DIP, than when programmed and ran under a non-kernel level implementation of IPC, namely MPI. However, although the cases for the kernel-level implementation of IPC, other parameters which may be important to high-performance computation, apart from efficiency of IPC, like extensibility, security, ease of use, etc., need further investigation.